Now we remember from elementary algebra that if we take the number, say, 2 and multiply it by itself and then by itself again, of course that is 2 to the power 3. And the 3 here is called the exponent, and it's the power to which the number 2 is raised. So multiplying again by the same number raises the power. 2 to the power 3 becomes 2 to the power 4 by multiplying again by 2. And conversely, if we divide by 2, we get from 2 to the power 3 down to 2 to the power 2. And if we keep on with this, following this logic here, if we divide again by 2, of course we get 2, but we can also call that 2 to the power 1. And if we keep going, dividing by 2 again, we get 2 to the power 0. And 2 to the power 0, by this logic here, is 1. And of course, we take that as a general result that any number to the power 0 is 1. So x to the power 0 is equal to 1. And so we can keep going. 1/2, which is 2 to the power 0 divided by 2, we can write as 2 to the power minus 1, just taking another 1 off the power as we divide by 2 again. And we can keep going for further negative powers. 1/2 times 1/2, which we can think of as 1/2 squared, is just 1 over 2 squared, of course. And it's also 2 to the power minus 1 divided by 2, so it's 2 to the power minus 2. So 1/2 squared, which is obviously equal to 1/4, we can also write as 2 to the power minus 2. Generalizing, for any number x and any power a, we can write that 1 over x to the power a is also x to the power minus a. We can also call 1 over x, or x to the power minus 1, the reciprocal of x. Here is the function of 1 over x, shown over on the right. You can see that it gets very large as we reduce x in positive direction down towards 0. In the negative direction here, it's a negative number, and it becomes arbitrarily large and negative as it approaches the origin, or 0, x equals 0. And loosely, we might say this explodes at the origin. More precisely, we should use the notation that it is singular at the origin. And this is an example of something we could call a singularity, which usually involves a function heading off towards infinity. In this case, it heads off to plus infinity on one side and negative infinity on the other. And incidentally, negative powers generally have this property of exploding as we get towards the origin. Multiplying a number by itself, of course, we also know is called taking the square. So here is x squared, that's x times x. And it's called taking the square because it gives the area here of a square with side x here. Now, we can also look at the square root. That's the opposite of taking a square. And for some number x, the square root of x here, that when multiplied by itself gives us x, is called the square root of x. So the square root of x times the square root of x equals x, of course. That's our definition of what we mean by a square root. For example, the square root of 4 is 2. This sign here is sometimes called the radical sign. And also we can write the square root with the radical sign, or we can also write it as x to the power 1/2. Squaring that gives us x to the power 1, which of course is x. And here's just a graph of the square root of x as a function here as a function of x. You'll see it does not explode anywhere, and it starts here at 0 and rises fairly smoothly with increasing x. Now, note that if the square root of x times the square root of x equals x, so also minus the square root of x times minus the square root of x equals x, because minus 1 times minus 1 is equal to 1. So although 2 is the square root of 4, also minus 2 is the square root of 4. And conventionally, we will typically presume that we mean the positive square root. So when we say the square root of 4, we probably mean 2 rather than minus 2. Unless we state otherwise, we mean the positive square root. But we should always remember that both the positive and negative versions of the square root are quite legitimate versions of a square root of a number. Now, Pythagoras' theorem tells us that the square of this distance here, the hypotenuse, is equal to the sum of the squares of this side and of this opposing side of this right-angled triangle. And so, equivalently, we could say that the length of this side of the triangle is the square root of x squared, the square of this side, plus y squared, the square of that side. And by convention here, we always take the positive square root. So r is a distance, and it is always positive. And in general, this process of summing up the squares and taking the square root, where we have distances that are at right angles to one another, is a general way of understanding a distance between two points. A very useful piece of algebra that we all know very well is how to deal with an equation like this. This is a quadratic equation. So ax squared plus bx plus c equal to 0. And the solutions, or the roots of this particular equation, are given by a very standard formula. X is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. So there are two roots, one corresponding to the plus and the other corresponding to the minus. This has a very simple graphical meaning. If I plot up the function x squared minus x minus 2 here, that's a function that corresponds to a quadratic if we set a equals 1, b equals minus 1, and c equals minus 2 in this formula up here. And then the idea of the roots is that these are the points at which this particular graph crosses through the origin. And of course, we have our formula here for figuring out the answers. And if we use that formula, we get two answers to the formula, 2 or minus 1. And indeed, we find this red curve here crosses through the horizontal axis at 2 or at minus 1. That's when this function is equal to 0. And this here is an example of a quadratic curve, also known as a parabola. Incidentally, we note that it's possible to factor this quadratic equation here into the product of these two terms. This one corresponds to the root where x is equal to 2, because if x is equal to 2, this term is 0, and so the expression on the right is 0. And similarly, this term corresponds to the point where x is equal to minus 1, because if x is equal to minus 1, this term equals 0, and so the equation equals 0. And as I said, this is an example, this curve here is an example of a parabola. Now we can go on with powers to raise a power, such as 2 to the power 3, for example, to the power 2, that is to square 2 to the power 3. Now we can write that out. It's 2 times 2 times 2, that is 2 to the power 3, times 2 times 2 times 2 again, which gives us 2 to the power 6. Generalizing, we can say that if we have a to the power b and we raise it to the power c, we simply have to multiply the b and the c together.